welcome to this MASTS webinar. It's titled Application of Peridynamics for Marine Structures, and that's with Selda Oterkus. Selda will give us a presentation, then we'll have time for questions. As I just said, we'll be recording the talk, but not the Q&A portion, so when we get to that bit, feel free to unmute and your camera on and get involved. Otherwise, you can pop a question into the chat and then I can read it out for you. I'll give a quick introduction before we start. So Selda is a professor in the Department of Naval Architecture, Ocean and Marine Engineering at the University of Strathclyde. She is also the co-director of the Peridynamics Research Centre. Her research mainly focuses on multiphysics modelling of materials and structures, including damage prediction due to various loading and environmental conditions. So without further ado, Selda.
Thank you much, Patton, for the kind introduction. So welcome everyone for my webinar. So as mentioned, my talk will be on application of peridynamics for marine structures. So before I start, let me give you a brief outline of my talk. First, I'll start by giving brief information about digital twin and structural health monitoring. And I will introduce you two different approaches that we are using, which are IFM and peridynamics. And then I will finish my talk with final remarks. So I'm the co-director of Peridynamic Research Center. So before I start my technical part of my presentation, let me briefly introduce our research center. So it's the first research center in the world focusing on peridynamic research. Of course, in addition to peridynamic research, we are also working on several other areas, such as offshore renewable energy, aerospace and marine structures, and both experimental computational hydrodynamics. And we are also focusing on sustainability and net zero technologies, fuel cells, battery technologies, and we are also looking at structural integrity, additive manufacturing, and robotic welding. So when we are considering about marine environment, we need to consider that when marine environment is a very harsh environment due to unexpected weather and sea conditions, and this can cause extreme and cyclic loading on marine structures. And this can, of course, create potential damage scenarios for our structures. And especially if we consider cyclic loading conditions, it can create fatigue damage. And moreover, since we know that the marine environment is very corrosive, it can also create corrosive damage in our structures. And our structures can really suffer from corrosion. And in addition to that, unexpected accidents like fire or kind of unexpected weather conditions can also happen during the operation process. And these damage scenarios can have significant effects on the reliability and integrity of our structures. Moreover, this can also create human and environmental safety, and it can also cause financial losses. So our aim is to prevent all these undesirable conditions. As engineers and researchers, we need to bring a solution. And one potential solution is the digital twin systems. And today I'm going to talk about this. And our goal is to develop a digital twin systems for structures which provides full field information about the structure in real time during the operation process. And it gives ability to predict any structural failure before damage occurs, and it works in harsh environmental conditions, and which produces reliable monitoring data for future design improvements. And digital twin is a very kind of wide concept, and it can be applied to many different fields. And in this webinar, we are going to mainly focus on its usage on structural health monitoring for marine structures. And if we consider for structural health monitoring, we need to consider that first we need to collect data from sensors which are located on the structures, and we need to process this data so that we can make decisions based on the data we collected from the structures. And then, of course, the structural health monitoring has two different phases we need to consider. First phase is to detect the damage, And there are different techniques that are available for this purpose. But today I'm going to introduce you IFAM methodology that we believe that it is pretty promising technique for this purpose. And second phase of the structural health monitoring, what we call prognosis, which means that once we detect the damage, to find out how the damage will evolve in the future. And today I will also give you a brief information about the method that we are using, Peridynamics, which will be beneficial for future predictions. And first, I would like to introduce you inverse finite element method, or in short form, IFAM. So IFAM was developed in NASA Langley Research Center for real-time monitoring of structures. Especially, it was initially developed for aerospace structures. It was developed around 2003. And then later on, we applied this methodology for marine applications. And the concept is pretty straightforward, actually. First, we need to collect discrete data, and usually this is the strain data from the structure. And then we process this data by using IFAM methodology, and then we convert this discrete data to full field information. So this means that we can have full field displacement information, or strain information, or stress information, depending on which data we are interested in, so that we can make decisions about the health of our structure that we are monitoring in real time. And there are many other techniques available for structural health monitoring, as I said, but IFAM has main advantages. First of all, the main advantage it has is we don't need to measure the loading. And this is you can imagine that in real time, measuring the loading is almost impossible, and especially during the operational conditions. And also, we can apply this technique for complex structures, like marine structures, and we can use this method for real-time applications, real-time monitoring applications, actually. And this is a simple representation of how we use IFAM. As you can see here as an example, we have a stiffened plate, and we located here some strain gauges on top of it. And let's say we are collecting discrete sensor data in real time from our stiffened panel. And you can imagine that our marine structures are mostly made of stiffened panels. Let's say this is one of them. And we process this data by using IFAM methodology. And at the end, as you can see, this discrete information we have will be converted to full field information. So even though we don't have sensors everywhere, we can predict the deformation or stresses or strains at anywhere in the structure by using this methodology, so that we can make decisions accordingly. Here, for example, this is one of the examples we have used before. This is a container ship, and this is the digital twin model of the container ship. And we don't need to put sensors everywhere because it's also unpractical to put sensors everywhere. For example, in this case, we put the sensors only in the yellow region shown in the figure. And you can see that this container, for example, the container ship is subjected to wave loading, for example. And here you can see the deformation, the stress distribution inside the material, inside the structure during the operation process. So it gives a full understanding of the structure, how it is behaving during the operation process, so that we can take decisions accordingly. For example, maybe we can put an alert system. We can say that certain regions are critical. Maybe we need to go and take an action accordingly. So next, I would like to briefly explain you peridynamics, which can be used for prognosis part of the structural health monitoring. Now we monitor our structures in real time, and we realize that there are some critical locations, and then we want to know what happens to these critical locations in future. For example, is it safe? Can we safely ignore this? Or what is the kind of effect in future? So for that purpose, we aim to use peridynamic theory for this. So what is peridynamic theory? It's a new continuum formulation, and it is a new because it's the type of equations that we are using are different than conventional continuum mechanics formulations. So, for example, in classical continuum mechanics formulation, we are using partial differential equations, but in this formulation, we are transforming the partial differential equations to integral form, which make it easy to use when there is a crack initiation or crack propagation. So basically integral forms are much easier to handle when there is crack in the structure. And we can also easily deal with multiple cracks, and these cracks can easily interact with each other. So since it is a classical continuum approach, so I will just briefly explain what is classical continuum mechanics is. It is widely used approach for structural analysis. For example, if you want to know what happens if you have a ship structure or money structure under different loading conditions, how it deforms. So which means that you can solve this equation to find the deformation in the structure. Although it's a very useful equation and we use this for finite element modeling, the software is using this equation at the background to find deformation. But when there is derivative in this term, as you see, this equation becomes invalid. So which means that we need to come up with another form of equation so that we can easily deal with cracks. So what we do in the paradigmatic theory, as you see, the term is replaced but with another term. Basically, what we are saying, actually the idea of classical continuum mechanics saying that we have material points in the structure and these material points only interact with the nearest neighborhood. But in the paradigmics, we just extend this theory and we said that it doesn't only interact with the nearest neighborhood, it interacts with all the material points inside the structure, so which makes it suitable for a new representation of equation of motion. So as you see, it's in integral form so that we don't have any singularity in the equation. And of course, we need to when we are considering this integral, we can use some numerical integration, but which represents the interaction between all the material points inside the structure. But of course, for numerical point of view, we may need to define a domain or horizon, which means we can say that out of this horizon, the interactions can be ignored. So here's just a small representation just to feel about how the paradigmatic theory works. You can assume that the material points are connected with springs, and once this structure is deforming, these springs elongate or contract, and once they exceed a critical value, they are broken. So which means that this is way how we simply introduce damage into the equation. So since this integral is represented by integration, so we keep track of each broken interaction so that we can have a damage profile at the end of the analysis. So this is just basics of paradigms. I have mentioned, of course, we have developed this methodology for complex loading scenarios or for multiphysics applications as well. So I'll just show you some applications of paradigm methodology. This is, as I said, the main advantage of paradigms is it is suitable for crack initiation and crack propagation. And this is just one simple exercise we have done to show you how we can predict failure. As you can see, there is a plate here and there is an initial crack. And what we are doing is we are applying some velocity boundary condition from top and bottom. We are pulling it with a constant velocity. For example, initially we pull with a 20 meters per second. And as you can see, we observe that the crack propagates in a self-similar manner. And this is actually what we observe also when we make a chance to test this structure. And what we want to do is also, we decided, let's increase this velocity and let's make it 50 meters per second. Let's see what happens. As you can see, we can observe this branching mechanism. And this is the actually fracture pattern that we obtain. And this is much more complicated than the previous one. And we call this pattern a branching. And actually, this is usually observed in the real applications as well, which is the dynamic fracture pattern. So in order to obtain this, we did nothing special. We only change our boundary condition and our formulation can successfully capture this behavior. So this is another benchmark case for demonstration purpose. Here we have the chance to compare one-to-one with an experimental study. In this case, there is a plate. This is made of PMMA and there is an initial crack. Actually, this was done by previous researchers. What they did, they changed the orientation of initial crack and they pull the plate diagonally and they observe how the crack will propagate. Here at the top, you can see when the angle is 0 degree, 30 degree, or 45 degree, they observe different fracture patterns in their PMMA material. And we did the same simulation by using our paradigm methodology, implemented the material behavior, we put the initial cracks, and as you can see, we capture very similar crack pattern by using paradigmic methodology. Maybe another simple exercise here. There is a plate with two nuts, and let's assume that we are hitting this plate with a hammer, and you would like to investigate how those nuts behave after the applied loading conditions. Here's just a video we have, I want to show you. So after we hit with a hammer, as you can see, crack propagates with an angle as shown in here. So the plate splits into pieces. Actually, this one as well, we have compared this with an experimental study. As you can see, the crack patterns are on top of each other. We capture almost exactly the same crack behavior. Of course, before doing crack analysis, we also verify our methodology with classical solutions as well when there is no crack. So we make sure that we can capture conventional solutions, and then we try to capture the damage pattern by using our paradigm methodology after we verify it. So as I mentioned, we have extended the paradigmic theory for different applications, and one of the applications we have is the corrosion damage, which is a very important mechanism, especially for marine structures. As you can see here, metals can really suffer from corrosion, and if you don't take any necessary actions, for example, it can reduce in thickness, or there may be local corrosion damage, as you can see here. And if we can do any improvement in the corrosion mechanisms, it will kind of help bring us significant benefits. And by using our paradigm methodology, we can simulate how corrosion starts and how it can evolve, so that we can take necessary actions before corrosion damage happens. For example, one of the most important corrosion mechanism is stress corrosion cracking, and this occurs when the structure is under tension and it's in corrosive environment, and usually these are happening in the microscopic level. Here you can see an example in the picture on the left, and there are different stress corrosion mechanisms, and the mechanism that we are investigating here is on the right is the hydrogen embrittlement, and we can investigate. Let's say you have a kind of a plate with a crack, and these are the colors are showing the microstructure, so we can go in the small scale. So in order to kind of simulate stress corrosion cracking, we want to also simulate the microstructure behavior as well. And each grain actually have different crystal orientations. So with the initial crack we have here, we assume that there is a corrosive fluid is kind of diffusing inside the material. So which means that we also simulate the diffusion mechanism by using our paradigm methodology. And as the hydrogen diffuses inside the material, as you can see with the red color, it makes the material more brittle and it creates new crack surfaces, as you can see, and new crack surfaces allowing the hydrogen to diffuse more. As you can see, we can keep track of hydrogen diffusion and crack propagation at the same time. And as you can see, this is the real scenario. Of course, it's not one-to-one exactly, but it can show you that we have similar damage pattern like in real scenarios. And another damage mechanism for corrosion is the pitting, which is a localized form of corrosion, and it causes material degradation. Again, for marine structures, this is another mechanism that needs to be considered, because it is the most common and most dangerous part of the corrosion mechanism, especially for marine and offshore structures. As you can see here, by using our methodology, we can capture realistic pit morphologies by using paradigm methodology. Why pits are important? Because, as we said, it creates high stress concentration, and when these structures are subjected to kind of loading, it will create this high stress concentration may turn into cracks. As you can see here, this is a real scenario where corrosion turns into crack, what we call pit to crack transition. And we want to also investigate this by using our paradigmic theory. Here, first, what we did, first we captured the pitting evolution here, as you can see here, corrosion pit. And then we assume that this plate is subjected to some tensile loading. And of course, we simulate the grains as well. Here you can see the grain. The colors are representing the grains. Actually, the white color is representing the grain boundaries. So in this case, for example, we have weaker grain boundaries. When this tension load is applied, there is a crack initiation starts, and then these pits turn into crack, as you can see in here. And as you can see, now with this methodology, we can predict crack initiation and crack propagation from the pit damage. And another mechanism that we need to consider for marine, offshore and marine structure is the fatigue, because our structures are subjected to kind of various loading conditions. It can be kind of cyclic loading as well. It is because the load is repeated during the operation process, and severe damages can happen, and which can also create major accidents. For example, ship structures, they are subjected to harsh marine environment, and due to repetition of loading caused by wind, wave, and current, and fatigue damages can occur in these structures. And another case is for example, ships navigating in icy waters. They are also subject to fatigue damage because there is an ice load acting on the structure as it moves through the ice. And also, these ship structures are made of welded structures as well, and they are inherently poor, but they have inherently poor fatigue performance. So we need to consider all these things. And we need an effective approach actually to estimate the fatigue performance of welded structures. So generally, and if you look at the literature, there are 3 types of methods that is used for fatigue damage predictions. And generally, fatigue failure can be divided into 3 phases. These are fatigue crack initiation, because under cyclic loading conditions, although the loading is not very high, because the material gets can get damaged, and it can create fatigue crack initiation. And the second one is the fatigue crack growth, and the third phase is the final failure. And if you look at the methods we have for fatigue damage prediction, the most conventional one is the ascent curve approach. But this one only provides the fatigue life estimation. For example, it will tell you after this many cycles or after this many years, your kind of structure will fail. But it does not give you any information about where the fatigue damage will start, how it will evolve, what is the kind of detailed information. We cannot reach this with ascent curve approach. As you can see, it's a very old approach as well. And we have also Paris law approach, which in this case, it only provides how cracks propagate due to fatigue. This means that you need to have an initial damage, existing crack in the structure, so that the method can work. So it cannot capture fatigue crack initiation, and it cannot capture final failure as well. So there are limitations, as you can see, in both those conventional methods. So we have also paradigmic fatigue model, which is developed in 2014. So it can represent entire fatigue damage evolution process, fatigue crack initiation, fatigue crack growth, and final failure. And here you can see an example. Actually, I will show it in the next slide as well. Here, for example, this is a welded structure. 2 plates are welded together. And here's the weld material. And this material is subjected to cyclic loading. And here's actually experimental test that they obtain this type of damage in their welded structure. And as you can see, we can capture very similar behavior, just like in experimental results. And actually on the top also we have another exercise where we have a plate with the initial damage. There was another experimental study where they investigated number of cycles versus crack length, and they obtained a plot. And we apply the same loading to our plate. As you can see, they are on top of each other. So as you can see, we can obtain much more accurate information. Actually, not just lifetime. Actually, we can also have an idea how the cracks propagate, how it can affect our overall structural integrity by using the paradigmic methodology. So since we are looking at marine structures and offshore structures, fluid structure interaction is another important mechanism that we need to consider. So for that purpose, what we extended our formulation for modeling fluid flow or for modeling thermofluid flow as well, so that we can, the main aim is to simulate all these multiphysics mechanisms in one framework so that coupling becomes much natural. Here, in this example, you can see we developed the fluid structure interaction model, and in this case, we used Peridynamics methodology for structural deformation plus fluid flow as well. And there is an example here. There is a water dam and with a kind of rubber gate. Because of the water pressure, the rubber gate deforms and it opens and the fluid flows out. As you can see, this is experimental observation, and this is how we obtain by using Peridynamics methodology. Of course, in this specific example, we didn't consider the failure of the rubber gate, but it can be implemented if needed. Then I will also show you how we can use Peridynamics methodology for damage prediction in offshore structures. So offshore structures are subjected to harsh marine environment, and they can be many reasons. It can be corrosion or overloading or extreme conditions. So as you can see, accidents can happen. So we want to also kind of have an idea how we can create our model so that we can have better understanding of these offshore structures. So just like finite element model, we have simplified elements, which are beam elements. We also come up with peridynamic beam model. So which means that it will have the damage capability inside. Here, we just a demonstration purpose, we have modeled a jacket structure, and we assume that it is subjected to some current and wave loading and wind loading as well. And here's the superstructure on top of our jacket platform. And we assume that, let's say there is an initial damage, and we want to see what happens if this structure is subjected to all these loading, how this behave. So we model this, we first developed the Peridynamic beam model, and we modeled this whole structure by using Peridynamic methodology. And here you can see our simulation results. So I'll just play to have an idea how it looks. As you can see here, as the wave acting on our structure, because of that initial damage, it creates collapse of the offshore platform. Of course, this is, as I said, for future prediction. So let's say maybe there is some part of our structures, there is initial damage, and we want to know what happens, how it will affect overall behavior. As you can see, we can use the Peridynamic methodology to have a better understanding before bad things actually happen. So in this specific example, we investigate what if our platform is hit by a ship. There is a ship and jacket structure interaction. In this case, we ignore the wave loading or wind loading. We assume that jacket structure is still, and then the ship comes and hits our structure. Of course, we only model the front part of the ship, and we assume that that part is rigid. As you can see, as the ship approaches to our structure, the red part is showing the damage. So it gets kind of collapsed because of the ship approaching our jacket platform. Of course, this model can be extended to kind of more complex real scenarios. So another mechanism that we want to investigate is the ice structure interaction, because as you see, the ice can interact with ship or offshore platform. So we want to have a better understanding how these behave, how ice behaves when it interacts with the structure. Here is an example that we consider. This was an experimental study that was done before. So we replicate their experimental work and we try to understand how the ice will break when it is hit by a rigid conical body. This is the ice plate, and this is a rigid structure that's hitting to our ice. Here you can see on the left, this is the experimental data. They observed the radial cracks and circumferential cracks when the ice plate is hit by a rigid structure. And we did a similar simulation. This is a rigid structure, and this is the ice plate. As you can see, we obtained the radial cracks and circumferential cracks that was observed in the experimental results. As you can see, we can get very realistic damage patterns. In this case, we ignore the damage in the structure, but that can be also implemented. So when they hit each other, both ice and both the structure can get damaged if you want to have further study. And we can also use peridynamic methodology for damage prediction in lithium-ion batteries and fuel cells. And as you know, low carbon shipping is an important concern, and battery technologies are becoming more and more important. And we are particularly interested in damage occurrence in electrodes in lithium-ion batteries and fuel cells. And for the durability of batteries, it's important to have the kind of defect-free battery components. So here we use peridynamic methodology to kind of estimate how these electrodes get damaged during the charging process. And we can also obtain damage initiation and propagation in fuel cells. Now the damage occurs at high temperatures. As you can see, we can predict the damage pattern in the fuel cells by using our peridynamic methodology. And not only for metals, we also extended the methodology for complex structures, for example, composite materials. And in this example, we investigate what happens if our composite structures is subjected to underwater shock response. In this case, actually, it's not the underwater shock that creates the damage. It is the generated shock waves due to this, and it can create severe structural damage. And by using peridynamic methodology, first we simulated the composite material. As you can see, this is a 13-ply composite laminate with different orientations. So we simulate this by using peridynamic methodology, and we assume that it's subject to shock loading. Here is our peridynamic results. As you can see, we can see the damage in each layer of the composite laminate, which is actually even experimentally difficult to observe. You can have the damage, but we may not know which layer get damaged. But by using our methodology, we can identify this damage. And this plate was kind of bolted from the circumferential. As you can see, these are the bolts. The holes are showing the bolts, and because of the shock loading, the red region is showing the damage or the radial cracks. And here on the right, you can see the experimental damage that they obtained by the previous researchers. And we also were able to capture similar damage pattern in our composite laminate plate. And also, fire is an important mechanism that we need to understand how it will affect our composite structures. So for that reason, we also simulate fire by using peridynamic methodology, but our fire model does not include chemical reactions. So I will say it is thermal and fluid flow. They are affecting each other. We assume that there's a heat source. Because of that, the temperature is getting higher. And we kind of find out the damage in the composite material by coupling those two mechanisms in the one framework. So I just want to show you some applications of peridynamics. Of course, these are not limited. With what I show in here, we can apply to many different cases, many different materials, many different structures. So if you are more interested in peridynamic methodology, we have a website, peridynamics.org. You can also have access to different resources. And also, you can also see this book, first big book on the peridynamics theory and its applications. And it's one of the last book, Peridynamic Modeling, Numerical Techniques and Applications. You can have more information. Or you can contact with us as well. So as a final remark, I explained two methodology where we can use for digital twin purposes. The IFM methodology is a new methodology and suitable for digital twin and structural health monitoring of marine and offshore structures during the operation process. And peridynamics is very suitable for predicting damage in various types of marine and offshore structures under harsh marine environment conditions. And the peridynamic methodology gives us a unique opportunity to virtually test our structures if they fail or not under certain conditions. And this will help us during the design process so that we can improve the safety and durability of our materials and structures. And thank you very much for your attention.